Hey guys, I'm Matt Johnson. I work in the Cloud CTO team for Cisco, and today I want to talk to you about container networking for real workloads and some of the work we're doing to change the way default container networking is done. So it's hard to say container nowadays without talking about Docker, so we'll start our story here with a little bit of a look back at the current status quo of Docker networking. So, quick overview for anyone that doesn't know. When you run a Docker container, you basically create a Linux bridge called Docker 0. And that Linux bridge gets an IP address on a subnet which isn't being used anywhere else on your host. And then every container basically gets an IP on that subnet as well through a little virtual Ethernet pair to that bridge on the host, which effectively means you have container to host networking. If you want access to anything running on that container from outside of that host, you're basically using IP tables, NAT rules under the hood to map the host's real IP on a certain port into that private network on that container. And why NAT? Well, because it works out of the box. If you think about Docker and think about their kind of rise to prominence, it's actually not really a technology company. It's just excellent user experience. You know, LXC, container virtualization already existed. Containers themselves are nothing new. The difference is that pre-Docker, it had never been that easy to use, explain, share, and build reproducible environments. So NAT made sense to them, for them. You know, they could guarantee that in 99% of deployments, or 99.9% of deployments, you as a developer wanting to install a Docker container on your host, it's going to work. The private network's going to sort itself out. You're going to share a few services through with the NAT rules that it would write for you. It didn't need to be anything more complex than that. But NAT and the default Docker networking stack is not without its limits. The container IP is tied to the host, and the services shared through are tied to the host's IP address. Because of that, and because you're sharing that host IP address, only one container can have a common port. So if I have a container running on port 80, externally that's used up the inbound port 80 NAT rule for that host's IP. So I can't have two containers running on a Docker host without implementing some kind of container-based load balancing listening on port 80. And that means you can either do careful manual port assignment, or you can do dynamic assignment, but then have the application have some code in it to actually support understanding on each instantiation of a container what port it's been given and do any maintenance it needs to do within the application to make that work. Also, applications need to query environment variables to find out their real IP addresses. If you have some kind of cluster code that's expecting to send a packet out and saying, oh, talk back to me on this IP, the IP it will see by querying Linux is the wrong IP. It needs to find out its host's IP from an environment variable. Again, it requires the application in certain situations to support understanding that it's running in a container. So a few kind of generations of work have been done on kind of changing the default status quo on kind of Docker's default networking. One is by Kubernetes. They created this kind of service, which is an IP-based resource which can sit above containers, and that service can be bound to one or more containers, basically acting like a load balancer, and basically allowing you to map multiple services in containers to an IP that you know is going to be a constant and is going to be fixed. And under the hood, basically they create a subnet per host, and there's a fully meshed GRE or VXLAN tunnels between those hosts, so that basically all of your Kubernetes nodes are in an overlay, and they can all get to each other and know how to route between those subnets. And tunnels are great, right? You know, they are used in Kubernetes because you don't have to deal with whatever the underlying network is. You're building an overlay, you know that all the nodes are going to talk to each other over that overlay. You know, it's a lot less complexity. Again, it's that usability, it's that works out of the box experience. You don't have to deal with the underlying network, but you do have to deal with on and off ramps. How do you get traffic in and out of your overlay network? Again, here you're going to have some dedicated nodes which span the overlay network and the real network. You're still most likely going to have to do some NAT in and out of those two networks, which means you're still doing the which ports have I already used on such an IP, which ones are mapping to which containers. So you still have some scalability issues and potential bottlenecks if you want to run a lot of traffic through, because you still have to solve the on-ramp and off-ramp problem. Depending on the implementation, you might also have quite a weird layer 2 design. However your tunneling mesh is set up or whatever technologies you're using there, you might have weird or lacking multicast support. It might treat broadcast strangely, and that might cause some problems when you're trying to put legacy applications that expect a regular Ethernet network up into a container. And you also have debug overhead. If you have 50 VMs fully meshed with tunnels and something goes wrong, which one of the 1,225 tunnels is causing you the problem? Last couple of things, it is a tunnel after all, so you also have to deal with MTU and fragmentation avoidance, unless you want to waste a load of CPU cycles potentially on fragmentation. And again, you could argue this or not, but there could be some security implementation issues, especially with kind of the layer 2 overlays where you're spanning up across a massive number of hosts. Considering that lots of people run privileged Docker containers when something doesn't work, it's like, oh, I need to be able to get to that network API. The solution is usually, run it privileged. So is that a really good security model when those people can then see that span dark network? So you might say, right, okay, so maybe tunnels aren't the best idea for various reasons. What about the future of Docker networking? What about this libnet Docker network thing we're reading all about and that's on GitHub? It looks really cool. It's going to move a lot of the network configuration into a network sandbox in the container, so there's a lot less interface with the host. But if you actually look, it's still very much based around kind of bridges and overlay, the kind of Kubernetes model. And also, call me a purist, but I don't really want my networking stack being brand new and only having 59% code coverage. So, maybe, that will become something to look into, but it's going to require a lot of time to bed in and iron out bugs, in my opinion. So, given those concerns, wouldn't it be great if we could do network containers without NAT, without tunnels, without on or off ramps, with a full IPv6 and IPv4 support, and know that it will scale to internet scale? And the answer is we can, if we stop treating containers as unique and special. Scalable data center topologies have existed for quite a while. This is a massively scalable data center design from Cisco in 2012. And don't worry, at this point, I'm not about to turn this into a Cisco sales pitch, I promise. But what I want to talk about is standards. There are already networking standards for doing networks at scale, for ensuring that some of the problems we've just talked about with kind of loads of tunnels and loads of NAT are solved in the data center. And these networking standards are tried and tested by the rest of the industry and already used every day at an unprecedented scale. My message here is kind of, we don't need to reinvent the wheel. We can integrate from the existing network team skill sets if we use some of these standards. And so this is our proposed solution for Docker and container networking. Basically what we're doing is using existing provable control plane, like BGP, to devolve routing down into the individual Docker hosts. We're layering some standards-based application policy on top for security, but effectively then each host becomes its own router, and because you have a shared control plane, every other host knows about the container's IPs on each host in a scalable manner, without overlays, without on or off ramps. The idea really behind this is to make containers a first-class citizen of the real networks that we all have today. We devolve routing down, we use BGP because it's proven, we use the Linux networking stack for the actual packet flow, and BGP is the control plane, which is proven. And the result of this is that containers have IP addresses. We don't need NAT, we don't need to worry about which ports are and aren't forwarded to a particular container. So DNS works properly because effectively a container is now just a host. It supports legacy applications and clustering because there aren't a real IP and a forwarded IP for each container. It supports multicast properly because it's just IP routing, and obviously IPv4 and IPv6 support. So we're using standard network protocols that the rest of the industry uses, and that also means that service providers and enterprises will find it really easy to tie containerized workloads into their existing infrastructure. If you buy today, we'll even throw in container mobility. And what I mean by this is, because we now have a control plane, it doesn't matter if a container comes down and gets rebuilt on another host. It can still have the same IP address because those IP subnets are not bound to what host you're on. And actually containerized data services that do clustering and expect to have free and open communication between nodes on the cluster are going to massively benefit from this. We're going to start seeing a lot more containerized data services, which currently we're having to do a lot of hacks to try and get working in a containerized environment. So where's this work going? You know, I believe in it. As I've just said, I think it's a sensible progression towards putting containers as a first-class citizen on the network. We've validated these ideas through other container industry supporters. We're not the only people thinking this way as kind of how we should start doing container networking. And we're actually working internally on the implementation of this now. Which brings me on to another note. And this is the part of the talk where I talk nothing about networking and just kind of take you off down a little other related tangent. Snowflakes. I want to talk about snowflakes. So whether you've heard of this or not, there was this big thing in the industry kind of, you know, before all this excellent kind of consumable operation stuff as a service where every team would build their own snowflake. They would build a unique infrastructure for running their product, right? They would tie together, you know, some internal code that they'd written, maybe use a couple of open source projects, but it would be nothing like any other team or any other company's way of deploying the same kind of workload. So everyone would end up with these snowflakes, which were internal technical debt. You had to pass on the knowledge of the snowflake from one person to the other when you were hiring new people. Snowflakes. And nowadays, we've learned, right? We've learned that actually we can all use these great open source tools in a very modular fashion and tie them together to all pretty much achieve the same results in our companies. So we might take a bit of Mesos and a bit of Marathon and some Consul and deploy those VMs with Terraform, and then, you know, we have something which we can deploy Docker containers on, and we might install Logstash and Elasticsearch to kind of take all the logs out of those containers and analyze that so we have something to give our ops teams. We might run it on Ubuntu or CentOS, but either way we're going to need to configure Mesos and Marathon, so we're going to use Puppet or Ansible or something like that after Terraform's created our VMs or provisioned our hosts. And we're all using the same tools, pretty much, give or take. But now we're creating glue flakes, because all of us are doing the integration of all these parts ourselves in our teams, and we're spending weeks and months going, oh, actually, you can't integrate etcd that way, that breaks, or this doesn't support that. So we're all ending up with the same technologies, but we're all implementing it in slightly different ways, just in the glue. And so that's why I want to talk about an open source project called Cisco Microservices Infrastructure. The idea of this is we are providing the glue. It's all the stuff that I've just put on the icons there, but it's written and in a way that if you deploy microservices infrastructure, we know that all those services are pre-configured to work, to scale, and are going to come up and work together. There is something to this whole user experience thing, right? That's why Docker took off so well. We're changing the name of microservices infrastructure to something less sucky soon as well, which is always good. And we're releasing microservices infrastructure 0.3 today. So please, I want to just say, go and have a look at it. Realize that if you're doing all this work anyway to support all these tools, we might as well be working towards one common set of glue instead of wasting a load of time before we actually develop our applications, gluing all these components together. Microservices infrastructure is designed to enable automatic deployment of all development dependencies. So it's based on Mesos, it's fully open source. We're utilizing the framework support in Mesos to deploy scalable data services and monitoring services and assurance services all alongside your container workloads by default. And as I said, the whole point is we've designed, written, and tested the glue. So consider contributing to this instead of creating a new glue flake all of your very own. We are really excited at the value of having an out-of-the-box environment for real-life workloads. The number of times you spin up a pass for someone and they're like, oh my God, this is great. Where are my data services? Like, this is designed to try and solve that. So back to that networking thing. You guessed it. The work we're doing on BGP and devolving routing down into the host is going into microservices infrastructure. It's going to be pre-configured to work out of the box with data and Marathon workloads, and it's at github.com/Cisco Cloud/microservices-infrastructure. And the roadmap and official announcements are going to be coming fairly soon. And thanks for listening. That's all I've got. And any questions?